Second law of thermodynamics. The Clausius statement, that's probably Greek to you. The Kelvin-Planck statement, more Greek to you. Irreversibility, yeah, I can see it. I put my car in reverse, I go backwards. Maybe I can understand that concept. Power cycles, we've been introduced to power cycles when we did energy conservation, but now we'll talk about the limits on that power cycle performance. Also, refrigeration and heat pump cycles we've been exposed to when we were doing energy, first law of thermodynamics, conservation of energy, but now we know there's a limit to the performance of those cycles. And we'll go back and talk about thermodynamic temperature scale based on power cycles and their limits, and how Kelvin came about with it, and that's why we have the Kelvin temperature to honor him. The Carnot, a French engineer named Carnot. Carnot cycle is like a theoretical maximum performance. We'll talk about Carnot cycle, where it's a closed system operating with air or closed system operating with steam. And then the Clausius inequality. So the inequality, that is the introduction to entropy, which is quantitative statement of the second law. So what's interesting about this chapter is people, Clausius, Carnot, Kelvin, Planck. So more names of people in this law chapter. What was our first law of thermodynamics? What was that? Well, even this textbook just bluntly states energy is conserved, and that's about it. That's it. But if you take a look at other textbooks written in thermodynamics in the 50s and the 40s, you'll see that they spent more time working through, let's say, energy can neither be created nor destroyed. Or energy can neither be created nor destroyed, but only altered in form. There's multiple forms for the energy. Or Keenan, who is one of the well-respected people who studied thermodynamics in the 40s. If any system is carried through a cycle, the end state being precisely the same as the initial state, he's defining a cycle, then the summation of the work delivered to the surroundings, the summation of the work delivered to the surroundings, is proportional to the summation of the heat taken from the surroundings. And why did they say proportional to? Because they were still working through a lot of it with the equivalence of mechanical energy and units of heat energy. BTU, reserved for the heat energy, and a foot-pound force, reserved for mechanical energy. But that's why they didn't say equal to, but it's proportional to. And yes, you can start with that and get to something like our first law, which would be a change in the energy is equal to, well, actually, let me back up. The change in all of the forms of the energy could be a change in internal, change in kinetic, change in potential energy is equal to Q into the system during the process minus the work out of the system. Is that a good first law? Sure. Okay, now let's talk about statements of the second law. Remember, those were word statements for the first law, and we turned them into equations. So we have word statements on the second law, and then we struggle with getting equations. But even this whole chapter is without equations. Next chapter, we'll get equations when we have entropy as a new property. Clausius statement. It is impossible for any system to operate in such a way that the sole result would be an energy transfer by heat from a cooler to a hotter body. That's our textbook. Another textbook, Brown. Heat will not flow from a cold object to a hot object without expenditure of external work. And another author, Short, he's actually from Austin when he's long gone, but in the 50s. Short was teaching there at Austin, UT. It is impossible for a self-acting machine unaided by any external agency to convey heat from one body to another at a higher temperature. Something about pumping heat up the temperature scale. Heat flows down from hot to cold. Does heat flow up? Not without some input into a system to make it happen. Not without some, this is a self-acting machine unaided by external agency. I can create a machine that's aided, paid for, and then I can make something cold or colder and make something hotter. But otherwise, no. So what about these words? What word did I highlight and underline and make bold in each of these? Impossible. Not impossible. Okay, anybody have like 2-year-old? What's the number one word you say to your 2-year-old? No. Do you like that? Do you think the 2-year-olds like that? Being told, no. Don't touch that. Don't do that. Don't run there. Don't touch. Right? Well, we as engineers don't like the second law either. And throughout the Industrial Revolution and a bunch, you'll see people fighting with the second law because you don't like limits. And we don't like limitations on our machines and performance. And engineers always are pushing the boundaries to try to get the best. Well, where's the goalpost? Where is the end zone? Well, the best is kind of like the maximum, and that's what they struggle with in thermodynamics back then. That's quantifying the second law. What is the best we can do? What is the limit that we can get up to but not go beyond? Where is it is now impossible. Well, here's Rudolf Clausius. If you notice, his name was at the beginning as well as the end of this chapter. And he published a work in 1851. You can still purchase copies of it and read it. It's been translated from German. But he was a German physicist. He was noted as one of the great minds in thermodynamics and won a Nobel Prize in 1918. These are the years that he lived. Posthumously, huh? What is that? Did I mess that up? Well, maybe they did give him posthumous. That doesn't make sense, though. I may be wrong on that. Okay. Yeah. So, oops. Here's you know what I did? I was thinking of doing? Forget that. Just go right there. It's Rudolf Clausius. Right? Well, I've tried to put it into, when I can just go out and put his name there. You can see when he was born, 1822, 1888, German physicist, mathematician. So I got the years right, I believe. And the country right. There's his picture. That's where I took it from. Let's see. Known Copley Medal in 1879, notable awards. Maybe he didn't win the Nobel. Somebody else may have won it. And you can read more about him and his work. Heat can never pass from a colder to a warmer body without some other change connected therewith occurring at the same time. There you go. See? On Wikipedia. True? So let's go on. So before we get to other statements, they struggled with it. Other statements of the second law, they done by other people, they had the idea of a thermal reservoir come into mind. So here is a definition of a thermal reservoir. An object can receive or provide large heat transfers without changing the temperature of the object, right? So usually we draw it like this. If it's a warm thermal reservoir, put it like this. Oh, it's at a high temperature, TH. Meaning if I take some heat transfer out of it, TH stays TH, right? I take a glass of water, I go down to the Gulf of Mexico, and I pour the glass of water in the Gulf of Mexico. Did I really increase the volume of the Gulf of Mexico, the amount of water in it? By that 1 cup I did, but it really didn't change the temperature or anything else, the water level, the Gulf of Mexico, right? That's the idea of a thermal reservoir. I can transfer some heat out, but the temperature isn't going to change. Does that mean energy came out of it? Yes, it does. All right. Also, you can have a cold thermal reservoir like this, TC, and you can transfer heat into it. Usually you dump heat off in the cold reservoirs So there you go. I mean, it's like walking outside, right? You have a breath, you blow hot air, you go, wow, I put out some heat, right, into the San Antonio environment. Did I increase the temperature in San Antonio? No. It's a small amount, didn't contribute. So now we move to the Kelvin-Planck statement, meaning that these two people around the same time come up with different statements which were essentially equivalent, so that instead of just saying it's the Kelvin statement or the Planck statement, give them both credit, the Kelvin-Planck statement, different people. It is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surroundings while receiving energy by heat transfer from a single thermal reservoir, meaning that I want this system right here to operate in a cycle. Often you put a circle indicating it's operating in a cycle, and it's producing work. But it's impossible to have that. Only a heat source and heat engine producing work. That's what he said. Let's read the next one. It is impossible to construct an engine which will work in a complete cycle, same idea, operating in a cycle, and produce no effect except to raise a weight and exchange heat with a single reservoir. So the exchange heat with a single reservoir, and here the work is going to be out here with the little pulley, and it's like turning that and lifting a heavy weight in a gravitational field. And that's one way of saying to do work. Produce no effect except to raise a weight. Raising a weight is work. Next one is impossible by means of inanimate material agency, to derive mechanical effect, that must be work, from any portion of matter by cooling it below the temperature of the surrounding objects. Some of these get pretty abstract, don't they? All right, something's limiting the performance. To have a good heat engine, you must have a sink. You must have a lower temperature, or what we call a cold thermal reservoir, and you want to convert as much of this QH into W, but you will have to, it's a restriction, dump some QC to a lower temperature body. You cannot have a heat engine running in a cycle operating only with one heat source, no heat sink. You have to throw some of that heat energy away, and that bugs people. It bugs people in the media, it bugs it bugs me, because we don't like limitations. We want to be able to convert all of that energy into the most useful form of energy. Well, you can't convert all that heat energy into work. There's a picture of Thomson. He's Lord Kelvin. Either you're Scottish or you're English, but anyway, I think Scots, aren't they going to vote to break away? They want to be a separate nation other than being part of the UK. I think there's a movement. Is it what? Ireland's been doing that for a long time. But I think Scotland may be voting soon to do that. Anyway, everybody wants to subdivide. And then Planck, German physicist, he's the one that won the Nobel Prize in that year, 1918. I copy and pasted, sorry. And those are the years, and you can read more about Planck and Thomson if you just Google them or go to Wikipedia. Now we move to the concept of reversible. A reversible process consists of a series of equilibrium states. So each of these states, it's a regular process. Each of the states in that process is an equilibrium state. So that if you stop the process, then you can go either forward or backward or just stay right there. If you want to go forward or backward, it's an infinitesimal urging to move it, not to move it out of equilibrium. It'll always stay in equilibrium. So how do you tell if a process is reversible? Well, a process is reversible if the system and all the elements of the environment, that means the whole world, everything, the surroundings, can be completely restored to the respective initial states after the process has occurred. So you think about it this way, plot it on some property diagram, PV, TV, PT, whatever. You start from initial state 1, you go to final state 2, and boom, now what you want to be able to do is turn it around and go back. If you could turn it around and go back, put the system back to where it was, and put the surroundings back to where it was, then theoretically that forward process was reversible. But it has to be frictionless. So what are the things that prevent something from being reversible? What are irreversibilities? Well, friction is your number one source of being unable to be reversible. It's irreversible. Heat transfer through a finite temperature interval. So if I have something here and it's hot here and it's cold here, and I have heat transfer from hot to cold, once that heat transfer has occurred, the cold isn't so cold anymore, maybe it's warm. The hot isn't so hot anymore, maybe it's warm. And I'd like it to go back the way it was. And you can't do that. It's irreversible. You can't get both. You have a warm coffee cup, right? You set it here on the table. You forget about it. You want to drink it an hour or two later. It's now lukewarm because it transferred heat into the room. You say, no problem. I'm going to put it back in the microwave and warm it back up. Well, that's all irreversible. But let's say I say no microwave. You can't do nothing but sit there and stare at the coffee cup. Is the energy going to flow back out of the room, make the room cooler, and the coffee cup warm again? No. Because the forward process, the initial cooling, was irreversible. Unrestrained expansion at lower pressure. Everybody likes to go around your birthday party, 2-year-olds, 5-year-olds, 6-year-olds, there's balloons, and some little joker goes around with a pin, and he pokes the balloon. And once there's a pop and that excitement dies down and a parent steps in and says, you shouldn't have done that, put the balloon back together again like you found it. That's an impossible task, right? It's unrestrained expansion. It's gone. So there are sources of irreversibility. The biggest one, you just blame it on friction. Just blame it on friction. Otherwise, Q through a delta T, or flow, let's call m dot through a delta P. Okay? Internal and external irreversibilities. It's where exactly do the irreversibilities occur? Do they occur inside the system, internal, or do they occur outside the system, in the surroundings of the system? And sometimes this being precise of where the irreversibilities occur is very, very important. And you can have them occur externally. What you often, when you talk about external irreversibilities, sure, it's the surroundings go on and on and on and on, but it's often in the very immediate location of the surroundings that you have heat transfer through a finite temperature difference or unrestrained expansion or friction. I know it's a little hard to grasp these theoretical concepts, but I make a bigger deal of this in Thermo 2 because you say, why is this system perform less or worse than this system? Why is its performance less? And then you have to look for where are the irreversibilities. Are they external or are they internal to the system? Sometimes they're external. So a Carnot heat engine. A Carnot heat engine was thought up by this man right here, Sadi Carnot. He's a military engineer in France. And he didn't win the Nobel Prize either. Because look at that. I definitely know he didn't live in 1918. But take a look at his years. He didn't live that long. How old was he when he died? 36 years old. Let's see. Well beyond, right? So you guys will be 36 or before you know it too. You think, oh, that's way out there. But anyway, he died young. He wrote a book, his only book that he ever wrote, in 1824. How old was he when he wrote the book? 28. Some of you are right around 28. All right? So that was his major life work that we still remember him by, that one book. But at that time, it was the beginning of the Industrial Revolution, and they were burning things to turn things, to lift a weight in a gravitational field. This was extremely novel. And as soon as they started burning things to turn things and lift things, meaning heat engines, they wanted to minimize how much they burned to do the same amount of lifting. And so a lot of people were looking at this, and they would make tremendous efficiency gains, because the thermal efficiency may be 0.01% on some of the earliest heat engines. You had to burn a bunch to turn a lot, a little bit. And so if you could double it, you cut down on the amount of coal you had to transport to feed the engine, the fire engine, the heat engine. And then they could double that again, and they'd double that again. So people were doubling things, and it was tremendous. It was a great time of innovation and huge advancements. But people were thinking like, okay, I've got the motive power of fire. I'm burning stuff, and I'm making the motive power, I'm making it do what I want, work. What's the limit? So he reflected on that. He thought about that, right? That's how they named this book or his paper. And it was a good piece of work, and people remembered it for a long time. But he had some ideas. He put them down like in corollaries. Here's one of them. He talked about reversibility, irreversibility, but the thermal efficiency of an irreversible power cycle is always less than the thermal efficiency of a reversible power cycle when each operate between the same two thermal reservoirs. So we have the same hot, TH, and the same cold, TC. Don't change hot and cold. All right? So if you have T hot and T cold, one of these is operating and it's a reversible heat engine, then I'm able to get more W out of it for the same QH. The thermal efficiency of the reversible is what I want over what I had to pay for. True? Here is an irreversible heat engine. It's operating between the same. It takes in, let's even think about it, the same QH to produce work, but that work IRR, irreversible, compared to reversible, gives me a lower thermal efficiency because I'm going to get less work out for the same QH. Another corollary, all reversible heat power engines operating between the same two thermal reservoirs have the same thermal efficiency. Once you've gotten to the max, you can't be more clever and exceed it by a different engine design. Okay, so if you're completely reversible, the inside of this box, the heat engine, how it works, okay, this could be design number 2, but it's completely reversible. The thermal efficiency of a completely reversible heat engine of design 2 will be the same as the thermal efficiency of a completely reversible design 1. So those are the two Carnot corollaries. How do we apply this to something? Take a look here, applied to a refrigeration and a heat pump cycle. Remind ourselves, you have a hot source or a sink, and you have a cycle, a system operating in a cycle, and you have low temperature, TC. Here, for refrigeration and heat pump, you're bringing it out, QC into, you're spending work to accomplish it, and you're dumping QH off. True? What was the coefficient of performance for my refrigeration system? It was what I desire over what I had to pay for. Make sense? And if I wanted to, I could replace by a first law. The first law says that W plus QC is equal to QH. So QH minus QC is W. So I could rewrite that coefficient of performance only in terms of Q's. Okay. The coefficient of performance of an irreversible refrigeration cycle is always less than the coefficient of performance of a reversible. Same idea that we had for the power cycle. COP, refrigeration, reversible, is going to be greater than the COP, refrigeration, irreversible. Friction is no good. Source of irreversibilities, get rid of it. Heat transfer through a finite temperature difference, it's irreversible, no good. You want to minimize friction, you want to minimize Q through a delta T. All right? Same with pressure. Flow, unrestrained flow through pressure drops, you want to minimize that. All right. And then all reversible have the same coefficient of performance as long as you don't change the temperatures of your thermal reservoirs. Keep those temperatures. Otherwise, you're not comparing apples and apples and oranges and oranges. You start mixing the temperatures and then trying to make it a comparison. The temperature differences make it. So if I'm trying to pump heat from, let's say, 300 Kelvin to 320 Kelvin, that's a lot easier than trying to pump it from 300 Kelvin to 500 Kelvin. That's a lot harder. It's going to be a lot lower magnitude on the best you can do, because it's a lot more significant delta T. Perpetual motion machines. So a large part of this chapter and the next chapter is talking about limits on performance of machines. And since the beginning of the Industrial Revolution, people have designed machines. Did I even tell you I had a visitor 2 weeks ago, maybe 3 weeks ago? He got rained out, and he said, "This has been keeping me up at night." He works in the oil field industry south of town. He said, "This works, and it's going to revolutionize engines in America. This is really good." I thought of it. I'm not telling a joke. This happens more than once. Did I tell you this or not? I'm going to go on. And so I said, "Okay, I don't have time for you." That's what I'm saying to myself, but I could tell he's very sincere, and he spent a lot of time driving up from his work because he got rained out, and he wants to share this idea. And often they want me to sign some confidentiality agreement so I don't steal their idea, but they don't know. They want to share it with somebody because they don't know what to do. They want to know what's the next step to take this idea, because this could be big, big, big bucks. And his idea was about engines and electric motors and stuff. And he said, look, you have a stator, and it's stationary. And then you have the rotor, and it rotates. And it takes power to rotate that rotor and create the magnetic field and all that. So I'm giving you the Cliff Notes version. It took me a while to understand what he's talking about. But he said, this shaft has to turn, and there's a torque in that shaft, and then the speed of that shaft, and then that's the mechanical power. He said, why didn't anybody think of this before? If I want to still have the relative motion of the stator and the rotor to be so much, don't leave the stator fixed. Let the stator, the outside part, rotate in the opposite direction, and the rotor in the inside, the opposite direction. They'll now rotate relative to each other at the same rate. And now you just cut in half, 1/2, the rotational speed. The rotors are going to be rotating at half the rotational speed. Okay? The torque, the power, you just cut it in half. The machines have now doubled their efficiency just by having a rotating stator, if that makes sense. I don't know if I explained it. I don't think I explained it well enough for you to grasp, because I don't want to spend much time on it. But I asked him, how much energy did it take to hold that stator stationary in the first engine? It don't take any energy. How much energy is it going to take to rotate that stator now in the opposite direction with half the revolutions that you want? Well, it'll be free, because the energy is all coming in on the shaft. It ain't going to happen for free, buddy. It's not going to happen for free. So anyway, but the idea of perpetual motion machines are out there, and there's plenty of them. And if you're going to be a mechanical engineer, you may have to think about this. So what we do is we have laws which try to, describe, this is a perpetual motion machine, and then we can disregard it. Years ago, it wasn't, the Patent and Trademark Office, I don't know what year they did it, but they finally declared, we will not issue a patent to anything that is a perpetual motion machine. But they had to struggle with, well, maybe a perpetual motion machine is possible. And it wasn't clear. And so even back in the 1880s, and people would claim, I have finally invented the perpetual motion machine. They would say that, and they would get investors to invest in them. All right, but anyway, so here's an idea. I have a water wheel, right? And so it rotates right here, and you dump water in the top of it, and the water's heavy on this side, and it creates a torque in this shaft. And so as long as I have a flow of water into this water wheel, it'll rotate, and I'll dump that water off to a lower lake, from a high source to a low source. Now, with that rotating shaft, I know what I'm going to do. I'm going to hook up a generator, and I'm going to make some electricity, and that electricity is going to come out, and that'll be perfect. And you know what? If I could get a steady flow of water hitting a water wheel to turn an electric generator, this maybe will work. But then the challenge is sometimes it doesn't rain, sometimes no problem. I'll pump the water up to the top of the water wheel. So every now and then what I'm going to have to do is siphon off a little of this electric energy over to a pump. And the pump is going to draw the water out of the lower lake that I have to dump the water at the bottom of the water wheel, and then pump it up to the top of the water wheel. Got it? See how that's going to work conceptually? That's a perpetual motion machine. Because if you draw a control volume that goes like this, right? So the pump, the generator, the water wheel, the lake, blah, 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 is all within it, right? What do you have? You just have free-flowing energy coming out of a box perpetually. And so what does that violate? It's a perpetual motion machine of the first kind because it violates this law. The first law, meaning that this energy is not, it's being produced. Energy is being produced in this design. Okay? I just threw that one together very quickly. But that's an idea of the perpetual motion machine of the first kind. Let's go, here's a man. He lived, John Keeley is a carpenter and a mechanic. He lived in Philadelphia. I did not claim that he's an American engineer. I did not claim that. These are the years. This is when you could still claim to have invented finally and mastered perpetual motion machines in the 1800s. You can read a whole bunch about him out there. Here's a picture off the internet in front of his machine. It's a hydro-pneumatic pulsating vacuum engine. It was claimed that you could run water to just a cup of water, a liter of water. It could move a train. In those days, trains were important, miles down the railroad track on a cup of water. And he had a lot of terminology and everything that. But unfortunately, when he died, they took a lot of his machinery and tried to reproduce it. Couldn't do it. He had he got millions of dollars, or the equivalent of millions of dollars today. A lot of money from investors. And this, I believe, is a picture off the internet of what was found in the basement of his shop, which ran little lines up to the top of his working area. And it was a big pressure vessel with they think it was compressed air. So somewhere in the system he had an energy source of compressed air, which would make the thing appear to work and demo in his facility. And the investors would come in, it's working. Can I write you another check? Please do. There's a few things I need to tweak. I'm only 80. It'll take me a while before right? And then he died, and they discovered it. So you can definitely go on the internet. Maybe I did pull up some of it. There he is, Keeley Motor Machine. And all this, there's a group of his board of directors. There he is. That's where I grabbed that picture. All kinds of great stuff and how it was investigated. And, oh, there's a picture of his lab on the second floor. And, oh, look at that. And then 3-ton sphere found in the basement of Keeley's laboratory building. What was that for, Mr. Keeley? I don't know. But it didn't work. Okay? Oh, what was here's a modern perpetual motion machine. Just go to YouTube and you can find opportunities to invest your money. Type car run on water. And there's not just one or two of these. There's not just one or two of these. There are, where's my car run on water? Oh, well, it's page after page after page. I'll have to go back because I don't have it. It's, sometimes it's in India and Bangladesh. Sometimes it's in, Florida somewhere. And they always have it. You just take that jug of water, pour it into your engine, and this guy's got 183,000 views. Those are a lot of views. And I'm telling you, it's the piles of it. Piles of it. All right? It's not trivial. Oh, I forgot to mention my other perpetual motion machine of what they call the second kind. So the perpetual motion machine of the first kind violated the what law? First law. This one will violate the second law. And so often what they do is they have a boiler and they transfer heat from a burning fuel into a boiler and they make steam. And from the steam they take it out to a steam turbine. And from a steam turbine, typically you put it to a condenser, dump off that heat, and then took it to a pump, and the pump up and over. And so this is the condenser, this is the steam turbine, this is a pump, and this is how we make a lot of electricity in America today. This works. It's rejecting some Q to a lower temperature, let's say lake water or atmosphere. True? Here you're burning coal to make that fireball in a boiler. So this is a true story too. Some guy drove up from Corpus years ago and he says, I don't know why, but these people, I understand how they make electricity in power plants, and it's really pretty stupid. And the reason it's pretty stupid is this is waste. That's stupid. That's waste. So, get rid of that. I'm a clever engineer. So I know that I need to condense the steam, but I also have to heat up the water after the pump. Heat exchanger right here. This is a great place for a heat exchanger so that I will be able to condense the steam right here. So this will be liquid coming out. It'll be condensed. And it'll preheat the feed water before it goes into the boiler. Smart! I'm a millionaire. What law does it violate? Draw a little. Here's your workout, right? Go a little control volume like this. You have only one Q in. System cannot operate in a cycle and produce work. Which one was that? Clausius or Kelvin-Planck? It was a 50-50 chance. Kelvin-Planck. I know I'm not. Terrible, terrible. Was it Kelvin-Planck? It's Kelvin-Planck. True? All right. Clausius is something about high temperature, low temperature, and you can't get it to go up without putting work in. And it's a cycle. It's operating continuously. You can get things to happen a little bit, but not continuously. All right? All right. So car runs on water. Don't invest. So the next one is very abstract. It's about temperature scales. Most of you just say, give me the temperature scale, I'll work with it. True? But there was a lot of thought that came back into temperature scales. They used to always be based on a physical fluid, water. Water is the common one because it's so common. And that's how you got the degree C, the degree F temperature scales. True? Somebody pegged it. Oh, that's when it freezes, atmospheric. That's when it boils, atmospheric. I'll go 0 to 100. But this is a different temperature scale. It's based on thermodynamics, not linked to substance. Not linked to water or mercury or anything else, how something expands or how some density changes. So it's independent of the property. What's it based on? It's based on heat engine ideas, based on T sub H, based on a heat cycle, an engine operating, and it's based on T sub C, and you make work. How can you get a temperature scale out of that? That's why they call him Lord Kelvin. He used to be Thomson. He was knighted, called Lord Kelvin. He's incredible. So the best I can do is I can say that early on people understood that if you had reversible, everything's reversible in this heat engine operating in a cycle, you would get the maximum efficiency. It would be maxed. Okay? And it depends on TH and TC. If I want to produce heat, if I get a higher heat source, if I burn it with a higher temperature fuel, it'll improve the performance, and they did. Or if they found if they could get it to dump off at a lower temperature, decrease TC, it improved performance, and that's great. So what they found was that the thermal efficiency was a function of temperature hot and temperature cold. So far, so good? Perfect. The next one, well, also, what is this equal to? This is equal to, by the definition, what we desire over what we had to pay for. What we desire, W, is what we had to pay for minus what we had to throw away over what we had to pay for, or 1 minus what we had to throw away over what we had to pay for. All that algebra makes sense? Good. So now what you do is you find that you consider this case. Same TH, right? And I'm going to put a heat engine operating in a cycle right here, going to an intermediate temperature reservoir, and another heat engine operating in a cycle, and finally going down to TC. And I'm going to compare that with one heat engine going all the way from hot to cold in the work put out. That's the logic. Do you see the logic? Instead of coming here and then here, then here, then here, I'm going to go here and then here. Right? On the right-hand side, one heat engine. On the left-hand side, two heat engines. But ultimately, they're fixed by TH up here and TC down here are the same. So if all three of these are reversible, heat engine, the first one, the second one, and the third one are all reversible, can you guess what the overall efficiency is from the side with two of them compared with the side with one of them? They're the same. That's a big conclusion. It's the same thermal efficiency. So take a look at trying to work this out. I'm going to have a little hard time here. I'm going to call this Q1, Q2. But that Q2 is going to be what's coming out because this is just a temporary thermal reservoir which is just going to pass it through, okay, at some intermediate temperature. So what comes into this one, the intermediate temperature thermal reservoir, Q2 from the first heat engine A, is what goes out to heat engine B. And then this is Q3. And for comparison, we just have over here, this is the same Q1, isn't it? Same Q1. And it has to be the same, let me leave it as Q3. That has to be the same Q3. All right? Same left-hand side, right-hand side have the same thermal efficiency. You feed it the same Q1 at the top, you're going to get the same Q3 out at the bottom. All right. So the efficiency of the first let's say heat engine A, is that going to be the work out of A divided by Q1? And the thermal efficiency of B, is that going to be the work out of B divided by Q2? Q2. Is that right? And then the thermal efficiency of C is the work out of C divided by Q1. That good so far? All right. So if you want what is the work A plus the work B, is that equal to the work C? You see that? This is the work C, that's the work A, the work out of B, right? So if I divide this by Q1, I'm going to put a Q1 right here, but what is this right here, this ratio? Work A divided by Q1. Is that the thermal efficiency of A? Yeah. And then this one, what is that one? Thermal efficiency of C. And so, but look at B. We have the, it's plus W B divided by Q2 over Q1. This is the thermal efficiency of B, thermal efficiency of A, thermal efficiency of C with this ratio of Q2 over Q1. And I think I even made it too hard on myself. Let me back up a little bit right here. I could have said this. The thermal efficiency of the left-hand side with the two heat engines A and B is equal to a function of temperature hot, temperature intermediate, and the function of temperature intermediate, temperature cold. And that needs to boil down to simply the efficiency on the C side, the right-hand side, which is a function only of the temperature hot and temperature cold. The intermediate is some figment. What Lord Kelvin deduced was this function has to be a function of a ratio of temperatures where you have all of these, the function of the hot temperature, a function of the cold temperature, function of the hot temperature, function of the intermediate temperature, function of the intermediate temperature over the function of the cold temperature. Otherwise, when they make the product, these won't cancel and you won't get what it has to equal on the right-hand side. So what he did was he looked at it and he said, well, I can see already that this eta is equal to 1 minus QC over QH, and that has to be a function of TH or TC over TH, TC over TH, it doesn't matter, TC over TH, function of CN, TH. And this one, you just do a shift of the function. Take that out, call it eta prime, a different function. And what you have is that the function of one temperature on the top divided by another function of the other temperature on the bottom is equal to the ratio of the Q's, so that they can be separated as just like this as a ratio, quotient. And he concluded that the simplest function he knows of is just an absolute T, and that introduced a new temperature scale. And so the ratio of the temperature cold to temperature hot is defined as QC over Q hot for a reversible heat engine. A man's life work I tried to summarize in 3 minutes. Good luck. I don't think I succeeded. I think it was a little more confusing than that. But what he did was he said for a reversible heat engine, that concept leads to a definition of a thermodynamic temperature scale, not linked to water, not linked to any other substance, but it's linked in an abstract way to a ratio of heat transfers through a reversible, impossible to construct heat engine operating between these two thermal reservoirs, one at Tc and one at Th. All right. Just tell me how to use the temperature scale and I'll be happy. So what he did was he said, we already know that the thermal efficiency is equal to 1 minus QC over QH. That works for any heat engine, but if it's a reversible, then it's the maximum thermal efficiency, and you can replace the ratio of Q's by ratio of T's as long as it's in thermodynamic temperature scale, Kelvin. Absolute temperatures. Don't put in degrees C or degrees F. So this was a great conclusion because it's so simple, yet it's so profound. It says that the maximum thermal efficiency of a power cycle depends on how far the temperatures are apart. So you want a large eta, make TH as big as possible. You want a large eta, make TC as low as possible. Here's a plot of increasing temperature TH for a fixed temperature TC. If you tried to have a heat engine where both of those temperatures are 300, there's nothing driving the heat transfer through the heat engine, the thermal efficiency is 0%. But if I increase TH, the thermal efficiency, the maximum theoretical thermal efficiency improves. So let's just say it's right here. Let's say it's a 500 Kelvin. Looks like it's around 40% thermal efficient. That means 40% of the heat from the high temperature source goes into work. What happened to 60% of that heat energy? Dumped to the low temperature sink. If you want to dump less energy to the low temperature sink, try to get the temperature of TH up. But you'll never get to 100%. It'll always be just a little beyond your reach. That's the Carnot efficiency for heat engines. You can do the same thing for refrigeration cycle and a heat pump cycle. Just make sure you go back and sketch. Okay, I have a reservoir, a system operating in a cycle, and this one I have to provide work. What I really want is a large QC, and I have to dump it all to QH. And so the coefficient of performance for refrigeration is what I desire over the work. I replace the work by first law. First law is QH is equal to work plus QC, so I can replace this is QH minus QC over QC. I want to get it into a ratio of Q's, so I'll say it's 1 over QH over QC minus 1, COP refrigeration. At this point, I'm going to say the COP, this works for any and all, but COP refrigeration, if it's reversible, is 1 over, I'm going to replace that ratio of Q's by a ratio of T's, if they're a thermodynamic temperature scale, and then unravel TC over TH minus TC. And that often you just say is the maximum or reversible or Carnot. That word Carnot is used to say, imply it's the maximum. So the Carnot efficiency for a refrigeration cycle is given by this ratio of temperatures. You could do the same thing for the heat pump. It's just algebra, very similar to what I've shown. Does that make sense? Yes, no? Let me continue then. This is where it gets more challenging. Sorry. Carnot thought of this power cycle. How could you make a power cycle operate and get the maximum efficiency? Theoretically, how could I put this together? No problem, he said. Look it. First of all, everything has to be internally reversible. None of that heat transfer through a finite temperature difference, none of that unrestrained expansion, none of that friction. So also, when you have the heat transfer with the surrounding, you have that heat engine. This is all TH up here. When you bring it into my system operating in a cycle, it's got to be brought into the system that's also at TH. I can't be having TH transferred into my cycle where it's a lot lower than TH. And when I transfer it out to TC, it has to be now the temperature at which the system's operating that I'm going to transfer it out has to be at TC. Otherwise, that's highly irreversible. Heat transfer through a finite temperature difference. And so they struggle with, how am I going to get this theoretically to work? Transferring QH, transferring QC to make W. Well, here's one way of doing it. Consider a closed system. Consider the working fluid being an ideal gas. We'll change some of these in a minute. But just start there. Get closed system ideal gas down. 4 processes. All of them are internally reversible. The first one, and it really doesn't matter where you start, it's a cycle, but start from state 1 and go to state 2, and the gas is compressed adiabatically. Okay, adiabatic, I forgot, what does that mean? No time for heat transfer, Q is 0. And the temperature jumps from TC to TH. Hey, that's how they're going to get that fluid to change the temperature. It jumps up from TC to TH. When it's now at TH from state 2 to state 3, it expands isothermally. Isothermal, it's always at TH from 2 to 3. It's staying at 2 to 3. And it's expanding. An ideal gas, as it expands, heat's going to be dumped into it. That's how they get the QH. All at TH. Isothermal expansion. I didn't say it was easy. I said it's theoretical. So you're receiving a large QH from the reservoir TH. Then, from state 3 to 4, that process, you expand adiabatically. No time for heat transfer. You expand it. The ideal gas temperature is going to go down as well as the pressure. But now the temperature just reduced to TC. Now I want to squeeze some heat out, isothermal compression, and it rejects QC all at TC. So I'm bringing in it all at TH into the working fluid and taking it out at TC. This is a picture of it. I take a piston and a cylinder. Process 1 to 2, the piston gets raised. There's expansion. And as it's raising, there's a large Q coming in. So that's our process 1 to 2, isothermal expansion. All at temperature TH. The temperature is constant and it's always high temperature. We stop right at 2, no more heat transfer, it's insulated. We go from 2 to 3 and you quickly expand it, no heat transfer. The temperature drops from TH to TC. It's a change, adiabatic expansion. Now the piston's way up here. Compress it, so the volume's going to be smaller. And as you compress it, have a heat transfer out, and the temperature's constant, isothermal compression. Then 4 to 1, more compression, and you're going to jump that temperature back up. There's no way this is going to be a power cycle. How can you get work out of it? All you're doing is heating and cooling and compressing and expanding an ideal gas. I'm glad you asked. We want to sketch this on a PV diagram to see how it might produce. So put it on a pressure volume diagram. You have 2 isotherms. This is a low temperature isotherm. This is a high temperature isotherm. So you start with a relatively small volume here and you compress it rapidly and it jumps to temperature. The volume went down from 1 to 2. Then you have isothermal expansion, 2 to 3. Then isothermal, this is isothermal. No, I should have started 1 to 2 up here, sorry. 1 to 2 if I'm staying true with my diagram. I start with isothermal expansion. Then I go adiabatic expansion. Then I go isothermal compression to 4. And then I go 4 to 1. It really doesn't matter on the numbering scheme, and you teach it out of a different book and they have a different numbering scheme, so. But there you go.
For process 1 to 2,
yeah.
It's compressed, but I can't conceptually see how the volume is increased.
Okay, 1 to 2 is isothermal expansion, and you're heating it up. And if you just heated it up at constant volume, the pressure would go up, right? So what's going to happen is you're heating it up to try to keep it at the same temperature. So don't let it conceptually be constant volume heating in your mind. Let it expand such that it's constant temperature. It's isothermal expansion, heating from 1 to 2. Now, 2 to 3 may be a little easier because you have no heat transfer and you're just rapidly expanding. The temperature and the pressure are going to drop. All right? Let's solve a problem. Here's air. It's an ideal gas. We'll use constant specific heat, C sub P 1.005. Molar mass 28.97. With the piston cylinder assembly, closed system, executing the Carnot power cycle. Carnot, 4 processes, all of them reversible. 2 are expansion, 2 are compression. 2 are isothermal, 2 are adiabatic. So you just put that together and you have your 4-process cycle. Okay? So during the isothermal expansion, the gas is heated at 700 Kelvin. Here's a table of states. And so state 1 is at 700 Kelvin. State 2 is at 700 Kelvin. 1 to 2 was my isothermal constant temperature, and the volume increased expansion. It's being heated. So sometimes it's very helpful. Make us a table of your states and list the properties. So state 1, state 2, state 3, state 4. This property is important. Temperature in Kelvin, pressure in kilopascal, specific volume, meters cubed per kilogram, and internal energy. Now that internal energy, you're saying, how do you get a finite value? What I did was I said U minus U ref. Okay, well, what is U ref then? It's going to be C sub P T minus T ref. Okay, great. But what reference temperature did you pick? Well, look at right here. This is 0 right here. For U, I picked 300. And U ref to be 0 at 300. So it's a very simple expression. U is just C sub PT, not C sub P. Why did I write C sub P? C sub VT, sorry. All right? That's all I did for the internal energy. Should I erase that? I already erased it, sorry. I'm sorry. Just leave it there. Okay. So that's how I calculate U. But it's always a change in U that's important. All right. So make a table of the properties like that. Okay, they give us some information. The gas expands adiabatically to 300 Kelvin while doing this much work. Well, just like a table with the states and the properties, you can have a table of processes. And so for process 1 to 2, what's important? Q, W, and the change in U. I'm really like writing the first law. The change in U is equal to Q minus W for the process 1 to 2. So I'm talking about Q1 to 2, work 1 to 2, and this delta U is U2 minus U1. So I put that in the third column, different columns. Does that make sense? It's so easy to become disorganized because you calculated something you don't realize you calculated. It's over half a page earlier in your work. So maybe make a table and populate it as you solve for things. Here what I did was I magically solved for all of the states. True? But I didn't magically populate the Q's and the W's and the delta U's. Right? And this one piece of information, 43.93 kilojoules per kilogram, I populated that as a given in my table. All right. Now, sketch the cycle on a PV diagram. What you would try to do, and this is going to be really hard to do, but it's helpful, is to try to say the pressure, what's my lowest pressure, my highest pressure? Well, it looks like I have a 25 kPa, 2,500 kPa pressure, right? Isn't that my max? So what I'm going to do is I'm going to start the pressure scale 0, 500, 1,000, 15, 2,000, 2,500. Got it? So I got it. I fit it. Now, how about the specific volume? What's my smallest specific volume? Something pretty small, 0.08. What's my largest? About 0.8. All right? 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. Barely fit it in. Right? Put your units meters cubed per kilogram. Put your units kilopascal. Now we can do a fairly good job of sketching it. Right? So where is 0.1? It's high pressure, 2,500 at the low. So it's right here, right there. It's right around there. That's 0.1. Agree? 0.2, 2,000 kPa. Okay. 0.1, it's right there. State 2. Make sense? Where's state 3? 300 down here and 0.83. There. I didn't quite make room for it. State 3. Where's state 4? 300. Hold it. That was no. It's 100. I'm sorry, 100. And this state 4 is a slightly higher pressure, and at 0.6 something. So it's 0.6, just a little bit higher. There's state 4. So it's hard to sketch these, but 1 to 2, 2 to 3, 3 to 4, 4 to 1. Yep, that's exactly right. If I go back and I look at this one right here, I grossly exaggerated how beautiful it looks. I did. But this is what they call, an illustration. And I'm trying to show what it might really look like. It's kind of slender and bent way over. This is an isotherm of 700 Kelvin. This is an isotherm of 300 Kelvin. And you're jumping between those two isotherms. Okay, 1 to 2. It stays on that isotherm. 2 to 3, it jumps down to the lower isotherm. 3 to 4, it stays on that 300 Kelvin isotherm and then jumps back up 4 to 1 to complete the cycle. All of these numbers work. They're good numbers. You can reproduce them. You have the skills. It's just not the time in lecture to reproduce them. All right. Now that we have the sketch, and if you don't like to try and draw it numerically accurately, go back and draw it like that. You say, okay, there it is. But here it is. Now, what is the heat transfer and the work for each of the processes? So what I'm going to do is I'm going to pause because I'm tired of talking, and I'm going to see if you can get some of these Q's and W's and delta U's. Can you fill up that bottom table? All right, so thanks for that correction that this really is for this amount of work is for the isothermal expansion from 1 to 2 at 700 Kelvin. So there we go. That's correct. Okay, so let's take a look at, can you calculate U2 minus U1 for this entry right here? What is it? It's 0. And this process 1 to 2 is adiabatic, right? What other process? Adiabatic. So can I put a 0 right there? So we have 2 of them in that table are 0. All right. How about the Q, 1 to 2? What value is that? What numerical value is that? I know it's kilojoules per kilogram. That's in the header. All of the units are in the header of the table. Yeah, you have to go back to the first law, pi for that process. This we already determined is 0. And this W is a positive 43. So this is 43.93 from conservation of energy for that process. Now 2 to 3, okay. What happens 2 to 3? I'm sorry. 1 to 2 is isothermal, and 3 to 4 is isothermal. 2 to 3 is adiabatic. Adiabatic. Okay, so for 2 to 3, adiabatic, which one of those can I put a 0 for? Q, W, or delta U? No Q. No Q, right? Now I gave a table of all the properties. So what's U, delta U? This delta U right here is U3 minus U2, isn't it? That's right. This is going to be negative 287.2. All right. How about the work? Write the first law down for the process 2 to 3. U3 minus U2 is equal to Q 2 to 3 minus work 2 to 3. That was 0. So is it a positive or a negative value? Positive 287.2. Right. All right. Now the isothermal is a little more challenging. It's really how this was computed. And you could compute that one. And so what I'll do is I'll show you how to compute the work 3 to 4. I have to make some room. Let me just erase right in here, please. All right. So now, how do I compute the work, the specific work 3 to 4? What's happening? It's isothermal from 3 to 4. 3 to 4. Isothermal, same temperature. And it's compressing, isn't it? The volume's getting smaller. Okay. How do I compute that work 3 to 4? Any suggestions? It's a piston cylinder apparatus. The volume's changing. Go back to the basic integral P dV. Now it is a lowercase w. It's everything's per kilogram. Everything's per kilogram. So I'm not doing the integral P d big V. It's lowercase v, specific volume. All right. How does the pressure change during the process 3 to 4 if it's isothermal? Well, it's always an ideal gas. PV is equal to RT at all times. It's an isothermal process. What about that temperature? It's the same. So is P equal to RT over V? And that T is a constant. R is a constant. 1 over V dV for the process. So this looks like it's going to be the natural log of the final volume V4 divided by the initial volume V3. You're integrating from 3 to 4. This RT, you could put P3V3 right there, right? You could replace the RT by P3V3. Or you could just leave RT, put RT3 there. It doesn't matter. A bunch of them will work. It's constant. What is R for the air? It's R bar divided by the molar mass. And R bar is 8.314, and you divide by 28.97, and you get 0.287, somewhere in that vicinity, kilojoules per kilogram Kelvin. So if I wanted to, I could do it that way, put an R with a T, or just put a P and a V, either one. So we would stick this value for P3, 103.36 kPa. This value for P3, V3, natural log V4 over V3. All right. What number do we get on that? It's on the next slide. I have to go to the next slide, okay? It's, what? Where does it go? Oh, I have to go to my Excel file. It's negative 18.8. True? Let's jump over back again. So this was negative 18.8. Why is it negative? It's not expanding, it's compressing. It's compressing. And then from the first law, this is also negative 18.8. There's some heat transfer out of it. Okay, 4 to 1. Write the first law for 4 to 1. Okay? And this is U1 minus U4, the final U1 minus the initial for the process, U4. And so 4 to 1, what is it? It's a positive 287.2. And what about the work? Negative 287.2. What's the work net for this cycle? I take all of these and add them up, right? Negative something. 25.1. Going to be positive net work. And then what about if I add up all the Q's? I'll get Q net. And Q net and work net better be the same. True? It's 25.1. So jump back to the Excel. So the sum here is 25.1 kilojoules per kilogram, and Q net is 25.1 kilojoules per kilogram. And for a cycle, is Q net equal to W net on good days but not all days, or some days, or no, like every day? Is this going to look for your errors if they don't sum up and then equal each other, okay? Q net is equal to W net for this cycle all the time, every cycle, refrigeration, heat pump, everything. Now, let's take a look up here. It says evaluate the thermal efficiency. So what is the equation for the thermal efficiency, and how would I calculate it? The thermal efficiency is what I desire. What do you desire for this cycle? A large work net. Okay, what do you pay for? A lot of students will put Q net, and then they'll get 100%, and they'll think, wow, that's a great cycle. But that's not what we have to pay for. What is it? It's Qin. All right. Well, in this cycle, where's my Qins? It's only 1 to 2. Q1 to 2 is my only Qin, right? Where it's positive, right? So if we put our numbers of 25.1 and then we did 43.93, you'll get some efficiency. I don't know what it is, some percentage. Now, somebody says, is this cycle completely reversible? Yeah. Is this a Carnot? That's what we're studying. Carnot power cycle using a piston cylinder apparatus with air as a working fluid. Can I use this very simple equation, 1 minus Tc over Th? 1 minus 300 Kelvin divided by 700 Kelvin? Will that give me the same numeric value? A lot of work, and this is almost too easy. Will they give me the same value? And they do. And the first time you do that, it's like, there's some magic going on. There's too many calculations to be consistent. But it is, okay? What did you get for the thermal efficiency? 57. And so when I went back here to the Excel sheet, 57.14, 57.14. Now we have the Carnot refrigeration and the Carnot heat pump cycle. We already worked out the efficiency, the COP, for the refrigeration, right? And I think it was the what was it? QC over QH minus QC. And then we replaced if it was a Carnot, we replaced by the temperatures Tc over Th minus Tc. And what it's saying is that's the best you can theoretically do. Everything's reversible, no friction. All right. You have to put in absolute temperatures, Kelvin. Can you put in degrees R? Yes. It's an absolute temperature scale as well. Clausius's inequality. This is the great introduction to the next chapter. It's an introduction to the concept of entropy. Clausius was a guy that did a lot in thermodynamics. And what he said was, after a lot of study, he said the sum of, that's the integral sign for over the entire cycle, the sum of, or the integral over the entire cycle of all the little, what is that sign? Heat transfers in, well, sign convention. If it's negative, that means it's not a in, it's an out. But if you take that and divide by TB, what? What is TB? It's the temperature of the boundary at which the heat is being transferred. So he said, if I have a system, I'm integrating over all of the Q's, okay, over the entire cycle, but I'm dividing by the temperature of the boundary absolute temperature scale, that will always be less than or equal to 0. Okay. He noticed also that when it's very, very less than, a very large negative number, it's showing us that it has a lot of irreversibilities. And as the number gets closer and closer to 0, it becomes more reversible. It's getting better and better and better. So what he did was he said, I'm going to let this be equal to a negative measure of performance of the cycle. A negative sigma of the cycle that will always be less than or equal to 0. And when this sigma of the cycle is equal to 0, that's the best we can do. It's completely reversible. When it's greater than 0, it's because it's there are irreversibilities present. Lots of them, lot greater than 0. And if it's less than 0, if you predict that this cyclic integral right here is less than 0, that just says you violated the second law. It's impossible. It's never been observed, and we would predict that it would not be observable because it would not work. All right, here's some questions. A reversible power cycle indicated by reversible, and an irreversible power cycle, indicated by IRR, irreversible, operate between the same hot and cold thermal reservoirs. How do the thermal efficiencies compare? So the thermal efficiency of the reversible is equal to the irreversible, or the reversible is greater. That's A, right? It's A. True? Now, whenever you see that you have A, B, C, D, E, think about it. You have to sometimes come down here. Could it be A or B? That would be, instead of this, it would be like this. Greater than or equal to, right? Could it be D? No. Because one has irreversibilities, that's why it's reversible. I mean irreversible. So it can't be that. It truly is A. But when in the rush, take a look at your other choices too, okay? A reversible power cycle, so again, we're staying with power cycle, it's reversible, and an irreversible power cycle operate between different. Change that word. Last time that word was the same. Now they operate between different hot and cold thermal reservoirs. How do their thermal efficiencies compare? And don't call it out, because I'm going to de-mic and walk around, and you just write it down each individually, A, B, C, D, or E. So when we mean two different reservoirs, your hot could be maybe 400 Kelvin hot, and this one could be 1,000 Kelvin hot. And you're putting something in between and something in between. And maybe this one is 300 Kelvin, and maybe this one is, I don't know, 325 Kelvin. All right? So if we have a power cycle, which one do you think is going to have a higher efficiency? The one with a delta T of 100 Kelvin, or the one of a delta T of, what is that, 800? No, that's not 800. 675 Kelvin. Which one do you... Even if this is a little irreversible, that could still beat a reversible, which doesn't have a large delta T. Right? Right? So you can go anyway. Oh, make this one the irreversible, IRR, put this one the reversible. Just switched it around. So if you start changing the different hot and cold thermal reservoirs, it's really hard to make a comparison about the thermal efficiencies. It's impossible. Did I tell you that one joke? It says, of all the companies, if you want to run a very profitable company in the world, what's one of the best, most profitable companies you could run in the world? A well-run oil company. True? All right. What's the second best type of oil? What's the second best type of company for profitability run? A poorly run oil company. I think I probably told you that joke, huh? Yeah. Power cycle operating between two reservoirs where one is 300 and the other is 900 Kelvin. Right? The cycle rejects 400 kilojoules, so QC is 400 kilojoules, and produces a network transfer of 600 kilojoules. How does the cycle operate? Is it reversible, irreversible, not possible, cannot be determined, either A or B? I pause and let you chew on that. Ooh. So I think it takes you a couple steps. First of all, can you tell what QH has to be? It has to be 1,000. And you have to do an energy balance over the overall system to see that, oh yeah, QH is 1,000. Once I know QH, I can actually get the reported thermal efficiency. What's the reported thermal efficiency? Well, the work over QH, it's 600 over 1,000, 60%. Well, what is the theoretical maximum, the Carnot efficiency? Maybe this one violates the second law. Maybe it's a perpetual motion machine, something like that. So we go back to Carnot for the heat engine, the thermal efficiency, 1 minus Tc over Th. So you put 1 minus 300 over 900. That's 1/3. So this is 2/3. The thermal efficiency maximum. The actual thermal efficiency has to be less than 66.6666 whatever, 7%. Is it? So what do you think? B? It's possible, and it has some irreversibilities. Okay, let's move on. A refrigeration cycle operates between two reservoirs. So we have 300 Kelvin for Tc, and then we have 315 Kelvin for Th. The cycle has a coefficient of performance, COP. What type of cycle? Refrigeration. It has a reported coefficient of performance of 6. How does it operate? Well, what we do is we say, okay, go back to COP refrigeration Carnot. Isn't that Tc over Th minus Tc? Okay, that's 300 over 15. And what's 300 over 15? 20. What do you conclude? So the maximum coefficient of performance theoretical is 20. You've got 6, so it's possible, and it's lower COP because of irreversibilities. Power cycle receives 1050 kilojoules of heat from a thermal reservoir. Last one of these. So the temperature hot is 900 Kelvin. And you have QH of 1050 kilojoules. And it rejects QC 300 kilojoules to TC of 450 Kelvin. It also rejects 250 kilojoules to one that's temperature is 350 Kelvin. Right? So we have temperature here of 450 Kelvin. So what I'm going to do is dispense with the C's. I'm going to call this, that's Q, you can call it Q1 from T1, Q2 to T2, Q3 to T3. All right? That makes sense? Does this cycle violate the second law of thermodynamics? Well, what we would say is the integral of del Q over TB has to be less than or equal to 0. Clausius' inequality. So let's just try and bust this into the sum of 3 heat transfers. We have Q1 divided by T1, and that's an N. That's a positive N. And we're going to have a negative Q2 over T2 and a negative Q3 over T3. And I'm going to compute that, and I'm going to see what that equals. Is it less than or equal to 0? So we have 1050 divided by 900 Kelvin. So each one of these has units of kilojoules per Kelvin. minus, because it's a transfer out, this is a 2 here, minus 250 divided by 350 minus 300 divided by 450. So I just have to compute that, and can somebody run that for me and tell me what that equals? Negative 0.5. Okay. Is that less than or equal to 0? It's okay. So it does not. Does this violate? No. If not, what is the thermal efficiency? Well, what is W coming out? What's W coming out? You do the first law, you see 1050 in, 250 out, 300 out. The rest of it had to come out. So this is 550 out. It's 500 kilojoules in work, true? And so the thermal efficiency is 500 kilojoules of work per 1050, a little bit less than 50%. Right?
That's about 0.2, negative 0.2.
Okay, negative 0.2. Thank you. It's still okay. I don't have time, but you can do the Carnot power cycle with water, not just ideal gas.
Will you be able to post this video before
I'll try.
Tuesday?
Yeah, I'll try. Thank you very much for your attention.